Here we are at section 8.5, which is areas of circles. But before we actually get to the notes on that section, let's take a look at how we can come up with the area formula for a circle, because it actually comes out of the formula for the area of a regular polygon. So if you want to take any notes on this particular part, you can. You don't have to. But let's take a look at our formula up here. So regular polygon area conjecture says the area is 1/2 times apothem times side length times number of sides, or ASN divided by 2. Remember, we also have this other version, which is the area is the apothem times perimeter divided by 2, because S times N, side length times number of sides, gives us the perimeter. Down below you see a bunch of regular polygons, and what I've sketched in here is the apothem, which is in red, so from the center perpendicular to the side, but I've also in blue sketched in a radius. Now the radius technically refers to if you have the polygon inscribed in a circle, then the center to the outside of the circle will be the radius, of course. So if you look at how that is represented on the polygon, that would be from the center of the polygon out to the vertex of the polygon. Now if you look at the apothem and the radius for each of these, going to a hexagon, a heptagon, octagon, nonagon, and decagon, you'll notice that the apothem and the radius get closer and closer together. So if we're already up at a decagon and the apothem and the radius are this close together, you can imagine what would be true on, say, a 20-sided regular polygon called an icosagon, or maybe a 100-sided or a 1,000-sided polygon. Those apothems and radii would basically start to overlap each other. And so the next slide here kind of shows that this is actually the 20-sided polygon, an icosagon. And it sort of looks like a circle, right? It's got 20 sides, so it's not a circle. But the more and more sides that you put on a polygon, the more and more circular it is. So we can start to blend the formulas together. This blue segment right here is the radius, and the black segment is the apothem. And notice how close they are together. All right, so as we add more and more sides, that apothem and that radius basically start to overlap each other. So let's start off with a formula that we already know. The area of a regular polygon is 1/2 times apothem times perimeter, or apothem times perimeter divided by 2 is another way of thinking about that. So we're using that P for perimeter in place of the S times N, but that is an area formula for the regular polygon. Now, what would be equivalent to the apothem in a circle? Well, as this gets more and more circular, as we said, the apothem and the radius basically start to get to be one single segment. If you had a 1,000-sided polygon here, you probably wouldn't be able to even tell the difference between the apothem and the radius. They would be so close together. So as it gets more and more circular, then let's actually replace the apothem with the radius, because they basically become the same thing for many-sided polygons. So our formula now is 1/2 times R times P. Now, what can you use for the perimeter of a circle? Well, the perimeter of a circle is pi times d, as you guys should remember, pi times diameter. We can also state it with reference to the radius, because a diameter is 2 times the radius. So 2 times pi times r is a way we can state the circumference of a circle also. So now our formula becomes 1/2 times r times 2 times pi times r. And now let's just rearrange the letters and the numbers. Since these are just 5 terms being multiplied together, we can do that in any order. So we can do the 1/2 times 2 times pi, which are the numbers, and then the r times r, which are the 2 variables. And simplifying that a little bit, 1/2 times 2 is 1, r times r is r squared, and voila, we have the area formula for a circle now, which is pi times r squared. And you can see the progression of how we came up with that formula from the area formula for a regular polygon. I think that's interesting, and I know there's a couple of you guys who followed along with that and think that's interesting as well. All right, let's actually do some problems now. The circle area conjecture, therefore, is the area of a circle is given by the formula area is equal to pi times radius squared, pi r squared, where a is the area and r is the radius of a circle. All right, so example 1, find the area Now notice the radius is given as 2 centimeters. So area is equal to pi times r squared. Plug in what we know, pi times 2 squared then. So the area is pi times 4. 2 squared is 4. If we want to leave our answer in terms of pi, we've basically got it now. So 4 pi. And so we'll write that. 4 pi, and we have centimeters squared. That's the unit, so square centimeters. Now, as a decimal, that's approximately 12.6 square centimeters. So that's an easier type of problem. What if you had example number 2, though? It says find the area, but notice you're not given a radius. You need a radius in order to get the area of a circle. Now, you are given the circumference in this problem, that is 13 centimeters. If we know the circumference, we can get the radius. So here we go. Circumference is equal to pi times diameter, pi d. In this case, we have the circumference. That is 13 centimeters. So 13 is equal to pi d. Doing a little bit of algebra, we're going to solve for d. So we're going to divide both sides by pi. Cancels it out. Unfortunately, it's not very nice looking here. We have 13 over pi as our diameter in terms of pi, which means that our radius is actually half of that. So 6.5 over pi is our radius. Now, we're actually not done with our problem, and I like to keep my answers in terms of pi until we're at the very end. And even then, sometimes we keep our answer in terms of pi. But 6.5 over pi is kind of a tough one to work with if we're plugging it into another formula. So I am going to take a look at the decimal there. 6.5 divided by pi is approximately 2.069, in this case, centimeters. So that's what we're actually going to use now. I'm going to try to squeeze in our area now of the circle on the other side here. So the area for a circle is equal to pi times r squared. Area is equal to pi times, all right, 2.069 squared. I know that's a little hard to read. That's 2.069 squared. And so when you punch that in, the area ends up being, actually we'll bring that all the way down here. Area ends up being approximately equal to 13.4 square centimeters. All right, so that isn't leaving our answer in terms of pi. We could have done that, but I think that would have been just a little confusing in the problem, and I don't want to get lost just because we're trying to leave our answer in terms of pi. So when we can, we're still going to do that. But this is approximately equal to 13.4 square centimeters. So it's like a two-step problem then. You've got to use the circumference to get the radius, then plug the radius in to get the area. So you'll have problems kind of like that. Example 3 is just a little bit more involved again. It says find the area of the shaded region. So imagine this is a circle with a hole punched in the middle of it, and the hole just happens to be a regular pentagon. So whatever is left, which is the shaded area, after we punch a hole in it, will be the area of the shaded region. So this actually is basically a two-part problem, right? We're going to have to get the circle area, and we're going to have to subtract out the hole that we put in there, so that's the pentagon area. All right, so the area of a circle is pi times r squared, and we're going to subtract off the area of our regular pentagon, which we know is ASN divided by 2. All right, I think we're given most of these things right here. We've got the side length is 10, we have a radius, which is 13, and we have the apothem, which is 12, and we're not given units here, unfortunately, but we will put in square units at the end. And so pi times r squared would be pi times 13 squared. Okay, the radius is 13. Minus ASN divided by 2, so the apothem is 12. Side length is 10. It is a pentagon, so the number of sides is 5. divided by 2. So doing a little work, this is 169 pi. 13 squared is 169, so 169 times pi, minus 12 times 10 times 5 divided by 2, so that'd be 600 divided by 2, which is 300. So 169 pi minus 300 is technically our answer in terms of pi, but that's kind of a weird answer in terms of pi. So if we're going to get the decimal equivalent to that, that is approximately equal to about 230.9 square units. Okay, so the area of the shaded region is approximately 230.9 square units. Notice that we didn't really round it until the end of the problem. We can't leave our answer in terms of pi. We want to keep it as exact as possible till the very end.